So they're recording. I'm allowed to say that because I'm from Nebraska, like Larry the Cable Guy. He's also from Lincoln, but Omaha-centric, actually. I lived most of my life within a 4-hour radius of Omaha, present life included.
Mm-hmm. Barely.
Barely, yes. But no, my record of getting to Omaha is 3:15. There may have been some speeding involved. But my son was asleep in the back seat, and I didn't want him to wake up. So I was like, we're getting home. You know how it goes. Anywho, we're talking about general linear model stuff. That's what we're talking about. Really, the focus here is on the linear models component, because by the end of the semester, that's something that I hope that you become very skilled at. And that's always how it works in terms of learning new material. It makes you learn the things you thought you knew better. So like in math, once you hit geometry, that teaches you algebra better, and then you hit calculus, and that teaches you, algebra and trig better and all that stuff. I remember that I learned more about English by taking Spanish. Yes. Because I had to learn what past participle was, and I had to attach labels to things that I didn't ever think about before. So that's one of the intents here. So we're reviewing things so that you get used to the way that I talk about stuff, because I will be internally consistent, I hope, in how I talk about things. And just in case it's been a minute since you've looked at this kind of stuff, I'm going to still operate under the principle that you do not have perfect and complete recall of everything that I've ever said or that you've been told. Should I continue to operate under that principle?
I am not Sheldon.
Yeah. All right, Zoomers, I'm getting the screen share going here. Let me know if we have any tech problems or audio problems with this. So slopes is what we're talking about, coding variables. In this case, we're talking about 4 groups as an example. So the point that I'm making here, back up to 11, let's say here. The idea is that if you have a categorical predictor, the most standard way of setting that up is what we call indicator coding, where each new variable that represents a group difference is binary. So you designate one group as your reference by coding all of the new predictors 0 for that group. That means the intercept is going to cover what that variable's mean would be. Then each of the other ones, in combination with each other, once they're all in the model at the same time, represents how far the alternative group is from the reference group. And we have to say it that way, otherwise the slopes are backwards. So it tells you, relative to the reference as a baseline, how different the other group is. So if the other group is higher, you'd expect a positive slope. If the other group is lower, you'd expect a negative one. So the model then tells us, through these linear combinations, that's the word you'll hear me say repeatedly, it's the idea that we combine fixed effects and variables to make something new. So beta 0 plus beta 1 times d1, so this would turn on to a 1 if we're talking about the first group, and it would stay 0 otherwise. That's why I have only this one in the box. Same thing with those. So the model's going to tell us how each alternative group differs from the reference, but we might want to know about differences among the treatment groups too. We can do that. The trick is that we have to recognize how the model builds a mean and then work backwards to figure out how that must imply a mean difference. So in this case, it works out that if I want to know treatment 1 versus treatment 2, I'm considering treatment 1 the reference of the comparison, so that's what gets subtracted as the reference point. The beta zeros drop out, and I'm left with beta 2 minus beta 1. So when you're looking at your output, you can do this in your head. And in fact, one of your Bridge 1's questions is talking about this. But why would you suspect? I don't want you to just do it in your head. What would we be missing out on? Like, I can tell you the difference between these groups is 3. I don't have a standard error. I don't have a hypothesis test. I don't have a p-value. So you can get your calculator out to check to make sure that your code works, because you should know what the result will be. But the point of asking the software to do it is so that you get those other pieces of information and you can report those additional effects. So I will show you various points during the semester how to do this kind of thing. Now, however, I do it the long way, like this manual way of setting up categorical predictors. There is a shorter way, and I deliberately hid it from you up until now. And I hide it from my other classes too. So the way that I teach coding categorical predictors in linear models like this is to manually create these binary predictors. The reason that I do that is because it directly maps onto the linear model representation. So we would need, if I have C categories, C minus 1 new predictors, and they are treated as quantitative variables. So that means in terms of syntax, SPSS syntax, they would be on the with line. This happens by default in Stata and R, and C dot, or SAS and R, excuse me, and C dot in Stata indicates a continuous predictor. So that's what I typically do. I also like it because you have complete control over what your predictors mean. Maybe this particular coding scheme, go back, is not as helpful, and you want to do a different one, like sequential coding. Come on. You can do it. You can do it. There we go, like this one right here. So if you have an ordinal variable, setting up your binary variables this way might be more useful because you get these successive adjacent differences. So there's reasons why I prefer to do it this way. In software, there's not always an option to do it the other way. So M+, for instance, has no way of saying that you have a categorical variable. You have to make the predictors yourself. But the other way is to let the program do it for you. And I will tell you that if I'm in a situation where I have a lot of groups, I'm going to switch to this because it's a lot less typing. So what do I mean by this? In SPSS syntax, it's putting a predictor on the by substatement, class variables in SAS, I dot in Stata instead of C dot, and what's known as a factor variable in R. So are you familiar with this idea, factor variables? You've seen this before. Not? If you haven't, it's fine. We're not going to do it this way. But I want to show you it in case you do it this way so that you can talk about what I'm comparing it to. So what the reference group is when you say, hey, can you make all those dummy codes for me, varies by software. In some packages, such as SPSS and SAS, the last group, numerically or alphabetically, is your reference. It's the first by default in Stata and R. So you have to know what your software is doing. This can be a lot more convenient in designs where you have a lot of groups and a lot of potential group differences that you care about. It also is more confusing because when you have interaction terms in your model, you'll end up with two different sets of results. One that are specific to the zero value of your interacting predictor, and others that are marginalized and conditional on the average. And so you can end up with like two different p-values in the same output file, and you got to figure out which one is the one you intended. So it's a lot easier to screw up, and that's why I don't tend to do it that way. But what is happening under the hood when you do this is that the program is creating binary variables for you that are internal to the software package. It's not putting them in your data set. And it doesn't leave one out. So it's going to make 4 new variables if I have 4 groups, where each one gets a 1 if it's that one and a 0 otherwise. So it figures out then how many of these are needed. If you have a fixed intercept in your model, which in most cases you will, then it leaves one out. And that's why different software packages have different reference groups. Which one did it leave out is the question. That's where it boils down to. So when you're using this technique in the syntax, it will look different because you have to tell it what to do for all 4 of these things every time you refer to this variable. So to me, sometimes it becomes easier to make it explicit with variables that you control and have access to than trying to figure out what's happening under the hood. Now, what about something that's a little bit of both? Semi-continuous predictors, or what is known as piecewise models in a longitudinal context. You're going to have one homework that uses this, I guarantee it. Homework 3, I believe, if memory serves, on counts. So this is an example of how many cigarettes have you smoked today? A count variable, actually, but it could be a predictor. So there are different kinds of people. There are smokers and non-smokers. And then among smokers, there's differences in the amount. So this variable is kind of both a group variable and a quantitative variable at the same time. And to me, there's a much bigger difference between going from 0 to 1 cigarettes than from going to 1 to 2 to 2 to 3, right? Like this demarcation is, are you a smoker or not? And then how much do you smoke if so? So I have 2 variables created that breaks this up into its component parts. So I have smoking status, 0 is no, 1 is yes. So that would give you the difference between smokers and non-smokers as one term. Then within the smokers, I've created a variable by centering this at 1, so that people who smoke 1 cigarette are the reference for this, and then this tells you what happens for each additional cigarette that you smoke. So this can be used for a lot of different variables. I also see this for things like childhood abuse, like how many of adverse events do you have, right? There's a big difference between none and something, and then there's further differences as a function of severity. So if you're interested in capturing both kinds of distinctions, you might consider a coding scheme like this. In this, I have examples in all three packages of how you would build variables like this. So R looks like this. We would start by making 2 empty columns. That's what NA means. The dots mean that in the other packages. And then I'm creating a new variable called smoker. If cigarettes is 0, gets a 0 here. Smoke amount gets a 0, because if you're not a smoker, you don't have an amount, but it has to be filled in for this to work. And then if it's greater than 0, smoker turns to 1, and the amount 1 turns to however the cigarettes are minus 1. So that then this is the reference point for this condition. And so it looks the same in the other packages. So you'll get a chance to practice this. I'm just kind of throwing it out here at this point, the idea that you can have mixtures of variables and deal with them this way. And Rebecca, you know this as a piecewise model in longitudinal. So does Vladimir.
We talked about piecewise last one.
Yes, we did, because I knew this was coming. And I knew longitudinal was coming. So yes. The thing about the intermediate class is that there were 3 of us who are teaching it, and each of us emphasizes extra stuff that's different than the others that we want to have for our future edification. So yes, we did do piecewise models. That's another way to think about this. All right, so how many slopes does each predictor need is an empirical question, often. So linear regression implies that we're looking at linear relationships, but you're not stuck with that. What linear actually means is that your model takes this form of slope times variable plus slope times variable. So we can have nonlinear relationships captured using a linear model. So for instance, if I have x and I add x squared, that creates a pattern like this, or a sad face like this. And you can have lines that sort of level off in the same way through linear and quadratic slopes together. A model that is truly nonlinear in the parameters is what they call that, would be something like this, where you have logs and exponents and stuff like that. So the role of each predictor in creating a custom expected outcome can be described using 1 or more slopes. So if you are interested in a linear effect of a quantitative predictor, that's just 1 slope. If you have a binary predictor, that's just 1 slope, because there's only 1 difference between 0 and 1. Easy peasy. More than 1 slope is needed to capture nonlinear relationships, so quadratic in this example of x squared, piecewise on the slide we just finished. For categorical predictors with C categories, you need C minus 1. The 1 is because you already have a fixed intercept. And in these situations in which the effect of a variable requires multiple slopes to fully delineate it, you're going to want to lump the slopes together to get a joint hypothesis test. So are there group differences, yes or no? That's 3 slopes to answer that question. There's 6 possible differences amongst 4 groups. So we will do that. Yes, sir.
2 questions.
Hit me.
When you talk about multiple slopes, is that multiple formulas or just all combined in one algebraic formula?
Great question. Multiple slopes within 1 model.
Okay.
So the idea is, let me see, do I have an example? Probably not. I won't. Let me go with, last semester, one of my examples was looking at the relationship between age and education. And 1 more year of education doesn't have the same consequence, right? There's a bigger difference if you go from like 11th grade to 12th grade, meaning you've graduated high school, than if you went from 9th to 10th. And then the same thing is true when you hit the next milestones of college, graduate degree, that kind of thing. So if I want to talk about, like, is education related to income? In the previous example, it took me 3 slopes to answer that question. So I would put all 3 slopes in the model, and I would create variables like this, where the parts of the variable are each represented by a different slope. So like this is a 2-slope example of how cigarettes would relate to some outcome. They both have to be in the same model at the same time for them to carry this interpretation.
This is
The same outcome. Yes, 1 outcome at a time so far.
Second question.
Okay.
Can you give an example of when we might use the quadratic or piecewise term?
Yeah. So quadratic is best for things that change direction in their effect. So there's a classic result in psychology about arousal and performance. So if you think about like being really, really nervous to do something, that's not great for your performance. Being really apathetic about it is not great for your performance. Somewhere in the middle is the sweet spot, so you do best somewhere in the middle, that kind of thing. For piecewise, anytime that you expect a different relationship in different regions of a predictor. So like in a clinical setting, there's a depression inventory that like if you get past 18, like you're clinical, and lower than 18 is subclinical. So if you wanted to answer questions about how depression relates to something else, you could make one slope for the clinically depressed people and be like, does it matter how depressed you are if you're in the bad region? That's one slope. And then if you're not in the bad region yet, how much does your depression matter in a subclinical way? So I can think of time as another example. So in the longitudinal class, if you have an intervention design where you have like business as usual, and then all of a sudden you change what you're doing and you want to see if the kids grow more after that point, you might have one time slope for the usual, another one for what the growth afterwards, and they would be two different slopes in the same model. Great questions. Other questions or comments? Zoomers, you can play too. I'm watching the chat. Vladimir's watching the chat. Yeah, I was gonna say, folks. So if you're sitting in this room and you're too shy to ask questions, log into Zoom and direct message Vladimir, and he'll read the question for you. Okay? You can be as shy as you want to, and Zoomers, you can talk to him too, and he'll make sure to get the question asked. All right. Come on, there we go. Giant slope. So the idea of lumping slopes together to answer a research question. You've seen this before, and we will do it this semester. So we can do this ourselves for instances in which it's not automatically provided for you. Here are some special cases in which it would be. So for a linear regression model, you get a test as to whether the model significantly predicts your outcome. Remember the letter that goes with it? Our friend F?
Mm-hmm.
Yes, I think maybe for Fisher? Internet, anyone want to check for me where the F test came from? I want to say Fisher did a whole bunch of stuff. He seems like the kind of guy that would name an F after himself too. So this test is essentially saying per slope, like what is the contribution of the slope to the model relative to what we know from it, relative to what is unknown. So this is where we were in sums of squares land in linear regression.
You were correct.
I was right? It's Fisher?
Ronald Fisher.
Excellent. The Google agrees with me. Not going to say it's right, just that there's consensus across multiple reporting things here. So we have how much information did the slopes capture in your model divided by k minus 1. So k is the number of fixed effects. The minus 1 is because we don't count the intercept. Then the denominator is how much information is left to be captured divided by how many more slopes you have room to add based on your sample size. So we can rewrite this in a different way. What you know over what you don't is the idea, and it's in a per slope metric. So F is going to disappear in this class to be replaced by its cousin chi-square, but it's the same idea. The difference is that there is no denominator degrees of freedom as part of chi-square. It's for infinite sample sizes. Yes? Yes, number of slopes times F is chi-square. Mm-hmm. Yeah, chi-square is not a per slope measure, whereas F is. So F is like standardized almost to be a per slope unit, and chi-square is not. So we have this thing called the F test that essentially evaluates how well your model did per slope. It's a test of your R-square being greater than 0. So we compute R-square this way in sums of squares land. It's based on sums of squares so that it doesn't go negative. Adjusted R-squared can go negative, by the way. That's one instance in which you might lump slopes together. In ANOVA language, have you heard the term omnibus? Like omnibus main effect, omnibus interaction? That's how I learned it. Vladimir's nodding. Does anyone else use that word?
In Ariel's classes.
In Ariel's classes, so design of experiments,
Yes.
causal inference, those
Yes.
ones, yep. So omnibus means lumped together. That's what it means. So you might have an omnibus test of group differences across the slopes that it took to differentiate the reference in alternative groups. You might also have an F for the change in R squared that results from adding things. So stepwise or hierarchical regression, where you have a set of predictors in one block, and then you add another set of predictors in another block, you'd get an F for the change in the R squared between those blocks, as well as within blocks as well. So there's specific instances in which you'll see this. It's a very common thing to need to do to lump slopes together to get a hypothesis test. Now the bad news. In generalized linear modeling software, this is almost never done for you. We're going to have to do it ourselves. And by do it ourselves, mean ask the software to do it separately with additional commands. So without denominator degrees of freedom, F turns into chi-square. So F times the number of slopes, which is numerator degrees of freedom, is what chi-square is. So the difference is the p-value because it's a different reference distribution. And if you're only testing one slope, t squared for that one slope is F. And analogously, when we turn t into z by taking denominator degrees of freedom away, z squared is chi-square. So there's like one slope or many slopes, and then are you using degrees of freedom or not? One slope is t or z. Multiple slopes is f or chi-square, respectively. Okay, switching gears a little bit here on this one. How are we doing? Can I get a thumb check? Some thumbs up, slightly sideways. Still, I'm going for anything above level. Level or above. It's a lot. Yes, questions?
Yes, Lisa, one. Can you repeat why in chi-square or c we don't have degrees of freedom in the denominator?
It's a distribution that doesn't change as a function of the sample size. So we're essentially assuming infinite samples when we use z and chi-square instead. If you have small samples, it's going to be wrong. So student T in that story, the guy who worked at Guinness Beer, it's a true story. The person who published the T distribution found out through trial and error that the Z distribution did not work for small samples. And so he came up like algorithmically with the right answer, which is T. All right, does that help?
Yes,
Maybe?
thank you.
Help someone at least, if not you. Yes, questions?
Is it also related to the fact that like chi-square doesn't use denominator degrees of freedom because it's not doing like the per slope thing like you were saying a minute ago? The F is standardized as a measure of effect per slope,
Mm-hmm.
but chi-square, like and denominator degrees of freedom relies on basically how many slopes you have.
Denominator degrees of freedom is mostly based on sample size. So it's n minus k because you can have up to n minus 1 slopes in your model. And it's like the question is, what do you already have there? So if you're not paying attention to that, then you're saying that the same reference distribution holds in all samples. And it's just not true. Like if you get into really small samples of like 5 or 10 people, it's not like where 5% starts in the distribution, like where you draw that line in the sand, needs to be a different place. We're going to ignore all that because the software doesn't care. Yes, numerator degrees of freedom is the number of slopes that you're lumping together in the hypothesis test. Yes. Yes. Indeed. Okay, other questions or comments? So taxonomy, how to think about what the slopes mean. Fixed effect is a term you will hear me say repeatedly. That refers to two different kinds, intercepts or slopes. You know what those are. Fixed means everybody gets the same. How you think about what the slope means, though, depends on the context of the model and what else is in it. So I'm labeling these things so that you have verbal labels to go with it, sort of like past participle and present participle and all those things when I was learning Spanish suddenly made sense to me. But what is more important is that you understand the ideas, and this will be fairly straightforward to understand. These are concepts that show up in Bridge 1 as well, so you get a chance to actually apply this knowledge, and we'll go over that. So all slopes can be described as one of three kinds. If you have a model with one slope in it and that's it, so x predicts y with one slope, the end, how I would think about that slope is it reflects the bivariate and marginal relationship between these two variables. Bivariate meaning two, not controlling for anything else, just straight up how related are these two things, and marginal meaning that that relationship is assumed to apply equally to everyone. Like if I said the slope of x in predicting y is 3, 3 holds across the board, regardless of your standing on any other predictor. And that's only 3 without thinking about any other variable in the problem. If you have a model that has more than one slope, the word bivariate goes away and would be replaced with multivariable if you wanted to do that, or multiple, either way. Then I switch how I think about the relationship, and the word that I use for that is unique. So if I have x1 and x2, the effect of x1 is whatever it brings uniquely in predicting y that x2 doesn't. Likewise, if I have x2, it's whatever it brings that x1 doesn't. Many, many synonyms for this exist. Controlling for, holding constant, adjusting for, partialing for. I just say unique because it's shorter. So you can have a relationship, say, between x1 and y that looks pretty strong, but you bring in some other variable and it might disappear because whatever it was doing is redundant with what you brought in. Then further within this, if the predictor is not part of an interaction term, then its unique effect is marginal, meaning applies to everybody. If it is part of an interaction term, then it is not only unique, but it becomes conditional and specific to the value of the predictor it interacts with being 0. So it's a higher level of conditionality. And the terminology that people use to go with this is simple main effects or simple slopes, which I tend not to use because I think it's offensive. You don't call something simple and make friends in life, because it's not simple. It's very complicated, actually. And this is the part that I find the most variability in when I teach these models as to how people have learned how to deal with this. So I want to spend some time on interaction terms. You're going to get very good at them by the end of the semester because they're very, very common in answering research questions. The kinds of questions that interaction terms answer is moderation. Does the effect of this vary based on other characteristics? Like, is the treatment always effective, or do people vary in how effective it is? Those kinds of questions. So trying to put this into a little more concrete terms in terms of the labels. If I have W here as a predictor, predicting Y, then I would call beta 1 its slope bivariate marginal because it's just two variables and this slope is thought to apply to everybody. If I have a model like this, so this would be an example where each variable has a linear slope only, then I would call them all unique. Like beta 1 is now the effect of W that is unique after controlling for x and z. It's what it brings to the table that they don't in predicting y. And the same thing would occur in terms of beta 2 and beta 3. But they're all marginal because if I want to say what is the effect of W, it's beta 1, period. That's the answer. I don't have to think of it any further. Marginal for everybody. Now if I have a model that looks like this, beta 4 has been introduced. This is an interaction term. It is still a slope, but it is the slope of two variables literally multiplied together. You do not have to multiply them. You do not have to build this variable. The software can do it for you. So beta 1, in terms of W, because W is not part of my interaction term, I give the same answer. What's the effect of W? It's beta 1, the end. I don't have to know anything else. In contrast, beta 2, what's the effect of X? Well, X shows up in two different places. I got to factor that into my answer somehow. So I would call beta 2's slope the unique effect of X that's conditional. The only circumstance in which the story ends at beta 2 for what the effect of X is if this part goes away. beta 4 xz would only go away if z is 0. So putting that all together, beta 2 is the unique effective x specifically when z is 0. Specifically. And you have to say it that way, because this model implies that if z were 1, the effective x would be different. If z were 2, the effective x would be different. Different in a systematic way, but different. Likewise, beta 3, same story in reverse. The only situation in which beta 3 conveys all of the effective z is if this part goes away, and now that happens when the other variable, x, is 0. So do these concepts sound familiar? A few nods. You can be honest if they're not. That just tells me like how much time we need to spend on them. Ish. That's what they say. Zoomers say, my audio froze at the start of the explanation for x. Can I repeat it? I will do my very best. We'll see if I can be internally consistent in how I say things. It's surprisingly challenging to repeat yourself exactly.
Very much so.
So in terms of x, beta 2 is not the effective x because x is also over here. So beta 2, the only situation in which the answer is just beta 2 in terms of how x relates to y is when this whole interaction part goes away. That only happens if z is 0 and it cancels this whole thing out. So putting that all together, beta 2 is the slope of x uniquely after controlling for all the other stuff in the model, specifically for people who have a z value of 0. The effective x would be some other thing otherwise. Okay, did that help? Okay, thumbs I'm seeing. Excellent. What about beta 4? How would I talk about that? Unique marginal or unique conditional? Oh, we got both
Marginal.
answers. It's tricky. Let me ask you this. Are there any other slopes in the model that are attached to both x and z at the same time? Nope. Therefore, marginal. So it's unique marginal, unconditional, in the sense that the interaction of these two is the same for everybody. How x and z moderate each other is the same for everybody. So that's why it's marginal. Now what we do with these numbers is the tricky part. You know where this is going. Okay, anything else out of that you want me to say again or say differently?
Just maybe in addition, just for those who are still recalling. So if there were an additional slope, beta sub 5, that was a product of w, x, and z,
Yes.
then beta 4 would be a conditional as
Yep.
opposed to a marginal.
Yes, that's like 5 or 6 slides from now,
Oh,
I
I'm
think,
sorry.
actually. But yes. Now, to your point,
Okay,
you're
okay.
right. But in order to have x and z and w in a 3-way interaction,
You
I would
have
also
all
have to have all the other
Understood.
2 ways underneath it. So then that would fill up the slide, and I don't have room for that. My slides are already packed as it is. But that's because I don't want you writing equations. I want you sitting and listening and thinking and writing down like connections that you're making to things. When I took classes, I hated it when people would write like equations in front of me because I could never copy it down in time, and I usually screwed it up in the process. And there wasn't Zoom, and there wasn't YouTube, and there wasn't ways to capture it.
Chalkboard.
Yeah, nowadays I see folks take out their phone and just start taking pictures of whatever I
film it.
drew. Yeah, well,
Yep.
we have the technology. I had a landline when these things were happening, so I haven't had one of those in a long time. Anywho, so interaction terms. Rather than talk about what the interaction does to y, the way that we talk about it is what it does to the other slopes for its constituent predictors. That's the switch. So I can think about what beta 4 does in 2 different but equally correct ways. I can think about how the interaction term changes the effective x as a function of what z is, or I can think about it as how it changes the effective z as a function of what x is. They're both right. So in phrasing research questions this way, oftentimes one makes more sense. People think about having like the focal effect of interest, and then they think about a moderator. Like, does this work? That's the effect. Does it work the same for men and women? Does it work the same in urban and rural schools? Does it work the same as a function of all this other stuff? Other stuff that it works the same as or not, those are the moderators. What you're caring about is the focal effect. And that is not a mathematical distinction, that's a substantive one. It's up to you. So how to figure out then what the model says these effects would be at any level is fairly straightforward. First up is to find all the terms in the model that have the predictor you're caring about. So for instance, if I care about what the effect of x is, that's what I want to figure out. I go into the model and look at where all the x's are. Don't need beta 0, don't need beta 1, do need beta 2, don't need beta 3 because there's no x in here, do need beta 4. So that's step 1. Step 2 is then to factor out the variable that you're caring about and stick it in the back. The brackets here of what remains, that's your recipe for how the model tells you what the effect of x is for anybody. It starts out with beta 2 for what it is if z is 0, when this part goes away, but then it picks up beta 4 as a function of z. So beta 4 is like a knob, like it's turning the effect of x up or down as a function of this moderator. And it's a knob that has the same click. Like each 1 unit change in the moderator clicks one more spot on the knob. I can do the same thing with the other variable too. I go up to the model, I find all the things that have z in it now. Bring those down, factor out z, and the ingredients of what's left tells me how I get the effect of z for anybody in my sample. And you can ask for these things. These are what's known as simple slopes or conditional slopes using various techniques in software. Every software package I know of has a way to do this. You just have to learn how to do it. So we're going to get lots of practice with this semester. The good news is that this becomes simple. I'm actually going to refine this slide. I always say there's 4 kinds of interactions. I'm going to say there's only 2. An interaction term makes your effect stronger or weaker. The end. Those are the 2 choices. Now, which pattern it is depends on the signs. If the sign of your predictor slope and the sign of your interaction term match, it's making it stronger. If the signs don't match, it's making it weaker. So more concretely, here's my model. Let's say that I care about the slope of x as the focal effect, and I'm thinking of z as the moderator. So let's say then beta 2 is 10. I would say, as x increases by 1, y increases by 10, if z is 0. If the interaction slope beta 4 were to be a positive 2, then what I would say is that the slope of x, beta 2 as the unit of the sentence that's being moderated, the slope of x becomes more positive by 2 for each additional unit of z. The signs match. So in English, I would say the effect of x is stronger in people who have high z levels. X matters more in people who have high z's. If you want to get into fancy GRE words, we could say something like the effect of x is exacerbated if x is a bad thing. The effect of x is enhanced if x is a good thing. Now let's go the other way. Slope of x is still positive 10, but now the interaction term is negative 2. So the way that I would think about this is that z is making the slope of x less positive as z increases. The signs are counteracting each other. So it's 10 if z is 0. If z is 1, it's 8. If z is 2, it's 6. So it's still a positive slope, but it's becoming less positive as the moderator increases, and eventually it will flip over and be negative. So this is an instance in which the effect of x is weaker in people who have high z. The effect of x is diminished. The effect of x is reduced. The risk of having high x is mitigated. in people with high Z. You can get as fancy as you want. But more positive, less positive, more negative, or less negative are the things that you want to lock in on. Now, last semester, in one of the review activities, formative assessments, I asked the question, what are the 4 kinds of interactions? And several folks went to ChatGPT, it appears, or other coursework to get the 4 kinds. So I got this plethora of answers, but they were the same. So I knew they had to come from somewhere. Okay? So as I got this back out this morning here, because I figured this would be good here. These are all the words that folks came up with that mean the same damn thing. Okay? Synergistic. The effect of the focal variable becomes stronger as the level of the moderator increases. Stronger. That's the word you need in that sentence. The rest of it is word salad. Okay? Enhancing. Stronger effects at higher levels of the moderator. Stronger. Strengthening. Non-crossover. Stronger. Matters more. That's all you need to know. Oh, but the other ones are even more fun. An antagonistic interaction. You're antagonizing your 4 variables. What are you doing? Weaker. The effect of the focal variable becomes weaker as the moderator increases. Weaker effects at higher levels of the moderator is a buffering effect. That's a psychology thing. Buffering hypothesis. I'm familiar with that. Weakening interaction. Yes, that one. And then reversing. Yes, because if something becomes less positive and less positive, it's eventually going to cross 0 and become negative. That's a consequence. The only one that I accepted as different is crossover. And that is only applicable to a binary moderator, where you'd have a positive slope in one group and a negative slope in the other. And that's where more or less positive negative starts to fall apart a little bit. So I'll accept this one as different, but it's so rare in practice that it's not something I usually need to worry about. So take your pick in how you talk about it, but just know stronger or weaker. Signs match, stronger. Signs different, weaker. Cool? Do you want to practice with this a little bit?
Yes.
Okay, I thought you might say that. We did this about 2 months ago in intermediate, so you might remember it or you might not, or you may have never seen it in your life. I'm hoping that folks don't remember it, so it's new.
I'm sorry. I'll be quiet.
It's okay. So here's what we're going to do. We're going to write an equation, and we're going to try to predict, based on hypotheses, what the direction of these things are going to go. And these are all examples that I've seen in research or other students have brought to me. So the first one was a pandemic hypothesis. Zoomers, this is for you. The hypothesis is that camera use on Zoom is related to better course grades, but less so in larger classes. That's what this person thinks. So let's build a model to evaluate that. So first thing I need beta 0. Can I just do B because I'm lazy? Is that all right? Cool. Okay. Now we have beta 1 times, what's my first predictor that I need to predict grades to answer this question?
Camera use.
Yep, camera use. Let's make that binary because your camera is either on or off. So we'll say 0 if it's off and 1 if it's on. Oops. I can never type in front of people, of course. That's a rule. What's next? Yep, class size. Let's say that we centered it so that it's the mean of that, so whatever a mean class size is. No idea what that is. It differs greatly across disciplines and graduate and undergraduate. What else do I need? Yeah, I need the interaction, because otherwise I just say cameras are good and large classes are bad, and that doesn't answer my question. So I need beta 3 times camera and size. And if I'm writing the complete equation, I'd throw an E at the end of it because everybody gets their own residual. But we don't need to focus on that part here. We'll just think about this as like y hat. Now here's what I'm going to do. We're going to replace the B's with P's and N's for positive and negative. So in average size classes, do you think that camera use relates to better grades? Guess how many cameras I see in front of me? 0. So clearly we don't think that. Now, I don't think camera use relates to better grades either, only if it is a proxy for attention or effort, right? I think you can be paying perfect attention but not want me to see what your bedroom looks like, or that you're in your pajamas, or that you have children running around in the back.
Would you think that we're not gonna, I don't ask to change, but if you were to do a real study, would you separate camera use by student and camera use by instructor?
I didn't think that was even a thing.
Some people, some people do the camera while they're teaching, but the others aren't. So they can see like hand gestures and stuff.
Beats me.
Okay.
I think it would be weird to be listening to like a disemboweled voice that without a face going with it, but that's what my YouTube channel is. So I don't want my face on the internet, right? Like there are pictures of me on the internet, but none where I'm like paused, like, mid-sentence or something. I don't want that in my life. So I don't know. Point being, there are a lot of reasons why one might not want their camera on that have nothing to do with their engagement. Could be bandwidth. Maybe your internet sucks and you can't put your camera on. Like, there's a lot of reasons. So I'm actually going to put like a 0 here. I'm going to hedge it. I know I just said P or N, but I'm putting 0. What do you think about the relationship between class size and grades in people who don't have their cameras on? Because that's what this would mean. Conditional on 0.
Can I clarify? Are we trying to replicate this person's hypothesis, or are we trying to? Because in their hypothesis, they would have it be P, right? Like, we're just trying to replicate the hypothesis.
That's true. That's true. If we want to stick with the hypothesis as written, then I would say positive. Turn your camera on, you get better grades. Okay. Thank you for that catch. I'm not representing the hypotheses faithfully.
Because, I mean, like, if our discussion is correct, then probably the E will be large with this model.
Mhm.
Because the model isn't going to capture
Yes.
all the reasons why people use their cameras, leaving out those other things like bandwidth and privacy.
Exactly. So I'd want to throw some covariates in there as to try to measure all that extra stuff that might relate to camera use, so we can isolate whether the camera is the thing that we actually care about. Now, this person is somewhat agnostic about the effective class size. Do you think that better grades are related to higher class sizes or lower class sizes?
To an extent.
Maybe negative, because you don't get as much attention from
Yeah, lack of individual attention. Sure, negative. Now, if this person is right, that camera use is related to better grades, but less so in larger classes, what sign would this interaction term need to be? Should we take a vote?
Sure.
Positive votes?
I think so.
Based off of their premise.
Negative.
You're asking us or telling us?
I'm taking votes.
Oh, okay.
Votes for negative?
Are we voting for our hypothesis or what we think matches their hypothesis?
If this person is right, what should happen? That's what we're voting on. You can think they're wrong, but like if the results are to support this hypothesis, what should the pattern be?
For their hypothesis, the interaction.
Well, since we make sizes the N2 is negative, then we have to reverse it to carry it out.
If something is going to matter less in larger classes,
The opposite was the individual.
yeah, this one it would have to be negative because you have a positive effective camera use that becomes less positive in larger classes. It weakens the effect of camera use, according to this hypothesis. The signs would have to be opposite to weaken an effect. That's the key concept here. And I would say less positive, because it's not necessarily that camera use all of a sudden makes your grades worse. It just doesn't help as much if there's a whole bunch of black boxes and you can't even tell whose camera is on. I heard a story on a podcast about a 16-year-old boy who wrote a computer program during the pandemic to log into Zoom, mute his camera and his microphone, and pretend like he was there while he was sleeping.
That's pretty impressive.
Yes, and the dad in the story wasn't sure whether to be impressed or horrified. Like, probably a little bit of both. So, clearly in that case, camera use is not a proxy, it's disengagement, but nevertheless. So, point of the story here, if camera use is related to better grades, but less so, that is a less positive hypothesis. The interaction term would have to be negative for that to work out.
And we predict this model to have a high degree of error because we predict they're leaving out a lot of other factors.
Yes, I've boiled it down to just the variables in the problem, but yes, you'd probably want to control for a whole bunch of other stuff. Yeah. Okay, want to do another one? So this hypothesis is that persons who are receiving a new treatment relative to an old one, so let's think like control versus treatment, decline less over time in health than people receiving the old one. What's first?
Intercept.
I need an intercept. I need a predicted amount of health for somebody to start this show. The "you are here" sign of the model. What's my first variable? Yeah, let's say we'll call this treat, whether or not. 0 if you're in the control, 1 if you're in the treatment.
Time.
Yeah, good. So this is a longitudinal example. Model for the variance would have to look a lot different, but we're just focusing on the fixed effects here. Now what?
Interaction.
I need the interaction. Okay? Now, if we're right, let's say that time is centered such that time 0 is when the study started and people were randomly assigned into treatment versus control groups. At time 0 specifically, should there be an effective treatment? Hope not, otherwise you screwed up your random assignment, right? Because at time 0, like what we're conditioning on is this is the effective treatment only when this part drops out. That has to drop out at time 0. And if I've set up my data so that time 0 is the first occasion where they haven't been treated yet, they've just like gotten started, then this should be a 0. What about time? This would be a slope for how much they change over time. Yeah, declining less is the hypothesis. So decline is what we're expecting. So maybe this is like as a disease progresses, your health goes down. The question is you're trying to stop that progression with a new medication. Ask your doctor if this is right for you. Now, this is the effective time for whom? For the control group, because that's when this part would drop out. So this is only the effective time if you're talking about the control group. And it would be a negative effect if the control group is going to keep on declining. But the treatment is supposed to help reduce the decline, weaken the decline. What sign does this need to be for that to be true?
Positive too,
Positive.
because that's going to make you not decline as fast.
That's right. Go down less over time. It weakens the decline that you would expect. Opposite signs. To figure out what the rate of change per unit time is in the treatment group, I would start with whatever that number is and add this one. Because treatment turns to 1, then that creates the slope for the treatment group. So this model is only going to tell me directly what the slope is in the control group. The interaction term tells me how different that slope is in the treatment group. But I don't know what it is in the treatment group. To get to that, I got to add these together. Okay, how are we doing? Thumb check? Oh, all the way up now. And now. So we had an intervention in switching from abstract terminology and equations, which made some thumbs go up and some thumbs go down. We call that a heterogeneous treatment response, I think. Zoomers are saying it. There's no thumbs down button, I don't think, on Zoom. I'm not sure. Yeah, a mad face or the poop emoji would work to convey that, I think. Or as my son calls it, moji poop. How about a buffering hypothesis? This is based on a friend of mine's dissertation. Stronger tendencies towards forgiveness relates to a reduced impact of stress on disease severity. So stress is less bad for you if you're forgiving. Yep. What's first? Stress. What's next?
Forgiveness.
Yep, forgiveness. Abbreviate that. And then we need the interaction term, right? Because otherwise this just says stress matters and forgiveness matters. Doesn't answer the question. Now, if she's right, what do you think about the effect of stress on disease severity? Is stress good for you?
No.
Generally not. I know there are positive and negative kinds of stress, but generally people refer to stress as a bad thing. So if severity is the outcome, meaning how bad off you are, what should the sign of the stress slope be?
Positive.
Positive.
Because you're increasing your severity.
That's right, you're increasing your severity. So you got to word these things in such a way. Are you talking about health or are you talking about illness? I'm talking about illness. How about forgiveness? Do you think that forgiveness relates to severity?
If so, they're probably thinking it should go down.
Yeah, forgiveness is supposed to be a good thing, right? So maybe you're not as sick if you're more forgiving, specifically when stress is 0, mind you. Now, for this to be right, for forgiveness to have a protective factor or to buffer the deleterious impact of stress, what's my sign? Negative, opposite sign. So I would say stress is less bad for you. Stress is less related to severity if you're higher in forgiveness.
So can we try to talk about the other interpretation for that interaction there? So would this mean that like the impact of forgiveness is more visible in people who have more stress as well?
Yes, so let me repeat.
It's like exacerbating the impact, the negative impact of forgiveness on severity if you have more stress.
Yes, so let me capture that for the recording and for the Zoomers here. So if we go the other way, like if a reviewer too is like, nuh-uh, you need to talk about your interaction as what happens to the effect of forgiveness. Okay, I'll do it that way if you'd like me to. So forgiveness is good for you. It becomes more good for you if you're a stressed out people. Forgiveness is more important in stressed out people. Because two negatives, in this case, strengthen the effect.
And could that be related to, I'm just trying to like interpret what we were talking about last semester with like certain treatments having more of an impact for people who started out more sick just because they have more way to improve. So if you're stressed, you might have more to forgive in your life.
That's possible. Yeah, like why this is the way it is, I'm going to leave that to the actual scientists that study these things. I'm just pretending at this point with my Excel sheet. But yeah, each of these things we could go the other way too. So in this case, we could talk about how the benefit of forgiveness, like that's how I would talk about more forgiveness being related to less severity. The benefit of forgiveness is enhanced, is stronger in stressed out people. We could do the other thing too, if I wanted to focus on the effect of class size, I would say that being in a larger class is even worse for you if your camera's on. That's what this would mean. This way, the effective treatment, which is 0 to begin with, is stronger over time. The groups spread out. So then treatment is higher in health by the end, and control is lower. Oh, this way for y'all. Hang on. There. Decline. My elbows aren't working. So yeah, you can go the other way for each of these. It's up to you. Usually one makes more sense in the way the question is worded. Do we have the energy for one more? I think we do. Diminishing returns as an idea. Spending more time rehearsing stops improving performance and might even hurt it at some point. Beta 0. What's next? Yeah, let's go with how much you practice or rehearse. Let's go rehearse. How much time do you spend rehearsing? If I can spell that correctly, almost. There we go. No, this is rehearsing time.
Oh, it's rehearsing time.
That's what I meant.
That's rehearsing time.
What's my other variable?
Performance. No.
Performance is my outcome.
That's your outcome.
This is kind of a trick question. It's a tie back to something from 45 minutes ago. Yes, it is.
Oh, because.
Yep. It's the parabola. So practicing is good up to a point, and then maybe more practice after that point is not good. That's a quadratic. Another way to think about x squared is as an interaction term. So there's only 4 kinds of quadratics too. They take your linear slope and make it more positive, more negative, or less negative. Yep. And by the way, the more positive, less positive, that language, I've had folks push back on that because eventually if something becomes less positive, it does go into negative and vice versa. But I will cite the Weather Channel as my defense. If you listen to weather forecasters, they will say things like, tomorrow it's going to be not as cold. Like if it's -10 and now it's 0, we're not going to call that warmer. Like the word warm doesn't belong in that sentence. It's not as cold. Same thing happens in the summertime. Oh, it's only going to be 85 instead of 95. It's not as hot. So to me, those are different things. Is something still going up but at a lower rate, or still going down but at a lower rate? Less positive, less negative. So this semester, we're going to spend a lot of time on interaction terms and examples because most hypotheses sort of lend themselves to that. It's a very common thing. What this is called is moderation analysis. People take workshops on this topic.
You led workshops on this topic. I think.
This shows up in my workshops, but I haven't done a workshop just solely based on this.
Okay, good, because you mentioned earlier how you gave many workshop presentations to help out with things.
Yes, I have done many, many workshops to pay the bills. Well, that's what happens when you buy a house as a junior faculty member that you can't really afford. Oops. In the height of the crash, right?
Oh, so you bought up here and then it went down
Yeah,
here.
it was great.
Oh, you can't even sell for it, even apart.
Yeah,
Oh,
so.
that's unfun.
Mm-hmm. No, but people do have like extensive workshops on moderation, and they probably get these words out to make it sound more complicated than it needs to be. But not me. Stronger or weaker? So there are, in your bridge explanation, or the bridge activity, like look for this, okay? Because the second model has an interaction term. So these are the concepts that will show up in that we're looking to see if you can put the numbers on. Yeah. So to recap, me back. I don't want this slide yet. Come on, come back, there we go. What the interaction term does is affect the main effect slopes. They don't affect y directly, they affect the slopes that are part of their constituent variables. That's how we talk about them. Because it's very common for people to look at this and say, well, beta 4 talks about what happens when both x and z go up. No, it doesn't, because you gotta factor in beta 2 and 3 as part of that answer. Beta 4 doesn't do that all by itself. That only works in 2x2 designs, where you're turning things on and off. So beta 4 changes the slope of x, it changes the slope of z. All right, questions?
Yes.
Yes.
So let's say that let's go back to that last example where we had our quadratic.
Okay.
Let's say that I thought that the rate of return was higher than quadratic, but also is sloped down faster than quadratic, and I want to go fourth power. Would I also have to include the third power in that? So I had to go, second, third, and fourth.
Yeah, if it changes directions twice, that's a cubic reversal time to the third.
I'm still thinking I think it's still doing that,
Mm-hmm.
but I just think it's going up faster than a parabola.
Oh, you need a different type of model then, because
Oh.
it's symmetric
Okay.
in how it predicts it. That would have to be a different kind of curve function for that. I'm not sure what it would be, but it would be a different one.
Okay.
Yeah, we didn't do the signs on this.
Oh no.
So let's say that this is, rehearsing is 0. Like it's uncentered. Like what 0 means is you haven't started practicing yet. At that point, is rehearsing going to help you? If you like at the lowest point of rehearsal time, like as you
Yes.
move up, like this should be a positive. More time should improve your performance. But if at some point more doesn't help and might even hurt, what's the sign? Negative. Yep.
Calculus.
Is that the same thing? Would it be the same thing for like pre and post intervention?
Pre and post intervention, can you tell me a little more? Maybe.
The outcomes, like someone's efficacy or whatever, and you give them an intervention, and then you want to see if the intervention changes things over time.
Mm-hmm.
Could
So-
you utilize this type of model?
In terms of the fixed effects, yes. But anything that is longitudinal, like this example here, you need something else besides E in the model, because you have to account for the fact that occasions come from the same person are going to be correlated, and an E-only model says they're not. So with respect to the fixed effects and the intercepts and slopes that I'm doing as the point, yes, it would be the same. The rest of the model needs to adapt, though. Okay, other questions? 312, we did it. We made it all the way through, what, the second week of classes?
Mm-hmm.
Woohoo! So next week then, let me get this, my orange stuff back up here. Put us all on the same page. Yep. Next week, on Tuesday, we will go over the bridge activity as a group. We'll talk about why the right answers are the right answers. And I should be able to show you like what people picked. Like, did most people pick the right answer, that kind of thing. So you can kind of get a sense as to how you're faring. I hope I should be able to show that. We're going to finish lecture 1, apparently. And we're going to start talking about binary outcomes. So I will let you know when new material is ready for that. And on Thursday, we have to meet on Zoom only again because I'm getting kicked out of this classroom for comprehensive exams.
You knew it would happen.
They let me know in December this time, which is an improvement.
That's improvement.
But I do know that. So on Thursday of next week and then at the end of March, I think, yeah, there's another day where the same thing is going to happen. So if I need to move to Zoom for any other reason, I will send emails and let you know, but you can always check on this syllabus. If you see these words, you'll know that you can not use this room this time because people will be in here. So you'll have to find another place to Zoom from, unfortunately. All right. That's it then. Thanks for being here. Thanks for playing along with my examples. And I will post this, by the way, after class. So you don't have to write this down. You can download it later for your own use. Okay? Cool. Have good weekends. Let us know if you need anything. Bye for now.
You did say that we